Hey students, welcome to lecture number 12 of Linear Algebra 2. So last time we talked about continuous dynamical systems, which looked like this. So we had some vector with function x1 to xn, and here we took their derivatives, and we wanted to solve this equation where A was some matrix with constant coefficients, and this we did by diagonalizing this matrix A, and then we saw we could reduce this problem to the n equals 1 case where we just have one function, and then this linear system was easy to solve because the solution was just given by these exponential functions. And today we want to talk about linear differential equations, which also involve functions and their derivatives, but instead of now considering n function and their first derivative, we will consider one function, but not just the first derivative, but all of its derivatives. So we will consider equations like this, where f is some function, and f prime is the first derivative, f2 prime is the second derivative, up to the nth derivative. And then you ask, if there's a given function g, and some numbers a0 up to an, how can we find a function f such that this equation is satisfied? And this we will do this lecture and also the next lecture. So, but first some notation. So these f's, we want to take the derivative. So this function will live in some space where we are able to take the derivative. So for this, recall the following space, which we mentioned at the beginning of the course. So by C infinity Rr, we denote the space of all functions from R to R, such that any derivative of this function exists. So this space is a subspace of all continuous functions, and often this space is called the space of smooth functions. And every functions we will consider in this and the next lecture will be inside this space. And also this space is a vector space with the usual addition of functions and the usual scalar multiplication. So now we want to say what a differential equation is. And for this, we first define the following. So we first define what we mean by a differential operator of order n. So by this we mean a map, which we usually denote by t, from the space of smooth function to the space of smooth functions, which is given as follows. So t of some function f will be given by a0 times f plus a1 times the first derivative of f plus a2 times the second derivative of f, up to an times the nth derivative of f. So this is the order of this differential operator, where these a's are some real numbers, and this last an here is not 0. So it's really the nth derivative is involved when we talk about a differential operator of order n. And in our case, this a will always be constant. So a more precise way would be to say that this is a linear differential operator of order n with constant coefficients. But in nature, you could also think maybe that these an are also functions. But we will just consider the case when they are numbers. And then a linear differential equation is an equation of the form t of f equals g, where t is now a differential operator like this, and g is some smooth function. And then such an equation is called homogeneous if this g is 0, or in other words, a homogeneous linear differential equation has a shape like this, that we ask the differential operator of some function f equals 0. And first, so t is now a map from this vector space to itself, but by definition we see that this is actually so remark that this is a linear map. So this you can check easily by the definition or by the properties you know of the derivative. So first notice that t is, so differential operators are linear maps. So this t is a linear map. And the second, so when we are interested in homogeneous linear differential equation, so meaning if we have a fixed a differential operator t, and we ask for all possible f such that t of f equals 0, then this means exactly we want to calculate the kernel of this linear map T. So solving a homogeneous differential equation, which I'll denote by dE, is equivalent to determining the determine the kernel, so finding elements in the kernel of this T, because this is exactly the definition of homogeneous differential equation. Okay, so let's do an example. So later we will see that this is, I mean, the homogeneous differential equation looks like somehow an easy linear differential equation, but the main strategy will be that if we start with some arbitrary linear differential equation, meaning someone gives us a G and a T, and we want to solve this, then to find all solutions, we will be interested in the homogeneous equation, and here we will just try to find one particular solution, and then combining these two solutions will give us all solutions for this linear differential equation. But let's first do one example, or two examples. So what would be an example for an easy differential operator? So for T, we will give it a special name, so we call it D. And by D we just mean the differential operator, so a map from the smooth functions to the smooth functions, which just sends an f to its first derivative. And this operator we already discussed in this course as an example for a linear map. Okay, so, and then we can ask what is the corresponding differential equation for this. So the differential equation Tf equals g. So if g is some function, and we ask now what is the solution of this differential equation, so we ask what function satisfies the equation that f prime equals g. Well, g is now, so g is an element here, and so this is f prime. And from calculus, you know, solving this equation here, that f prime equals g, just ask for an antiderivative of this function g. So this has the solutions that f equals some antiderivative of g. And in calculus you learn that if g is a continuous function, then the antiderivative always exists. And this is exactly here the definition of this antiderivative, that this equation here holds, that the derivative of f equals g. And so this would be a linear differential equation, and what would be the homogeneous version of this? So we would ask for the kernel of this map T, but in this case the kernel of this map, so which function, so if you ask what is the function such that its derivative is 0, and these are exactly the constant functions, so the kernel of this D is just the span of 1, whereby this 1 we mean the constant function f of t equals 1 for all t. And the kernel of this map here are all multiples of this constant function. Okay, so this is maybe not so an interesting example, but we will use this notation d a lot in the following. So what it would be another example? So let's consider the following differential operator t. We take d, so the first derivative, minus a times the identity. So in other words, t of f equals minus a times f plus f prime. And this we also write d minus a. So if we write functions, operators just with a number, by this we always mean that we just take the identity map and multiply with this number a. So now, what is the solution of this for the homogeneous equation? So what are the solutions for this? So T of f equals 0 means that f prime equals a times f, because we ask when is this here 0. And this we already had the last time. The solutions for this equation are exactly given by the exponential e to the at, where we can multiply with some constant c. And so therefore the kernel of this map, of this differential operator t, is in this case the span of this function e to the at. So these are all solutions to the homogeneous linear differential equation Tf equals 0. But now we can ask what would be the solution of Tf equals g for some g in the smooth functions. And so this you can check that the following, so f of t equals e to the at, and then I take again the antiderivative, but now I take it of this function here, e to the minus at times gt dt. So this here is a continuous function, and we can take its antiderivative and multiply it with e to the at. And the claim is that this function here satisfies this equation here, because you can check that f prime of t. So how do you take the derivative of this here? So here you need to use the product rule. So you take the derivative of this, which is a times eat, and here you just have the same gt dt plus, and then we take the derivative of this, but the derivative of this is just the stuff we have inside here, and then we multiply it with this, and e to the at times e to the minus at cancels out, so this gives 1, and we just have gt, so this is gt. And you see here, this is our f of t, and therefore this equation here reads that, so this is equivalent to f prime of t minus a ft equals g of t. And this here is exactly t of f. So this gives one solution of this non-homogeneous differential equation. And this here gives all solutions to the homogeneous equation Tf equals 0. And so what is now the main strategy? So if I ask now, what are all possible solutions to this equation here? Because here maybe you can check this is a solution, because this satisfies this equation. But how do I get all solutions? So are there other possible solutions? And the idea is now that all these elements here in the kernel I could add to this solution here, and then this will give me again a solution to this inhomogeneous equation. So this is the strategy to find all solutions for a differential equation like this, T of f equals g. So the idea is to find one particular solution. So let fp, so this p now stands for particular. So let this be a function such that this satisfies this equation, meaning that f, so T of fp equals this g. Then the claim is, then all possible solutions of this equation Tf equals g are of the form f equals this particular solution, so this one single solution we found, plus fh, where fh is now a solution to the homogeneous equation. In other words, this is an element in the kernel of T. So for example, if this is a solution to this equation, and if I add some element in the kernel, why is this again still a solution to this? Well, because T of fp plus fh, well, T is linear, so T of fp plus T of fh, and fh is an element in the kernel, and therefore this is 0. And this here is, because it's one solution to this equation, this is G, and therefore this whole thing is G. And this also works in the other direction, meaning not only is this a solution, but all solutions are of this form. So we have this one particular solution, and we can find all solutions by considering all possible elements in the kernel. And this follows from a more general statement, which is true not just for differential operators, but also for arbitrary linear maps. So therefore we have this more general lemma here, stating that if I have an arbitrary linear map between two vector spaces v and w, and now I assume I have a pair v and small w, such that f of v equals this w. So in our example, this t, this differential operator is our f, this v is our particular solution, and this w is our g. So this here means t of fp equals this g. And having one of this solution, then the following two statements are equivalent, that for any x such that f of x equals this should be a w here, sorry. So if I find an x such that f of x equals this w, this is equivalent to that this x can be written as this v, so this particular solution, plus u for some u in the kernel of f. And this goes in both directions. So this is so the proof of this is in the homework, exercise number 2. And one direction I already sketched before, namely that if I have one of this solution, then so if I can write x as this particular solution plus some element in the kernel, then as f of this x will be this w. Okay, but the other direction is also true, and this you should show in the homework. So let's use this idea or this strategy here to find now all solutions of one particular differential equation. So we consider this equation here. So the second derivative of f plus f equals 2 times t. So in other words, the differential operator we consider is d squared plus 1, where when I write d to the I always mean that this I apply this di times, and recall this d was the operator which sends f to its first derivative, and therefore if I apply it twice, I have the operator which sends f to its second derivative. So this operator t here is exactly, if I apply this to f, I get the second derivative plus f, and the function g in this case is 2t. So these two are given, which gives us this differential equation, and now we ask what are the possible solutions to this equation. And for this we first want to find one particular solution, and for this we usually need to guess, but there are also ways of good guessing, and in this case maybe it's not so hard to guess to find one solution, because here we have a polynomial, and maybe the first approach would be to try if we find a polynomial such that the second derivative of this polynomial plus the polynomials equals 2t. Well, And in this case, it's quite simple, because if I just take 2t, then the second derivative of this polynomial is just 0. So this is 0. And then, of course, 2t equals 2t. So one particular solution is quite easy to find in this case. And now consider the homogeneous equation. So we want to determine the kernel of this differential operator here. So in other words, we ask for functions such that the second derivative plus the first derivative equals 0. Or in other words, the second derivative is minus the first, sorry, not the first derivative, the function itself. So the second derivative of this function f should be the negative of this function. And in this case, you probably know some examples for this. For example, the cosine and the sine satisfies this equation here, because if I take the first derivative of the sine, I get the cosine, and then I take again the derivative, then I get the minus sine, and therefore the second derivative is minus times the sine. And therefore the homogeneous solution of this is given by some multiple of the cosine plus some multiple of the sine. And we will see that that these are actually all solutions. So this we cannot prove yet, but we will see this later, that the kernel of this t is exactly the span of the cosine and the sine. So therefore we have one particular solution here, and we have all elements in the kernel, and this gives us all possible solutions to this here. So the general solution is therefore f of t equals this one solution plus the homogeneous solutions. So in this case we can say it's 2t plus and then some linear combination of the cosine and the sine, where these c1 and c2 are some real numbers. And this gives us all solutions. Okay, and therefore some of the main task is to solve homogeneous equations and to guess correct particular solutions. And we will focus now on how to always calculate the kernel of a differential linear for linear differential operator. And we will see, but we will not prove it today, but this we will do next time, that if we have a differential operator of order n, then the kernel of this, the dimension, is always n. So in this example here, this is a differential operator of order 2, and we see that by assuming that this theorem, that here we already have all solutions of this homogeneous equation, because here we have a two-dimensional space, and for this you need to check that cosine and sine are linearly independent. And this we will see in general, that for all differential operators of order n, we can always find n linearly independent solutions to the homogeneous equation. Okay, and so how do we find these n equations? So for this we introduce the following. So let t now be a differential operator of order n, meaning we have numbers a0, a1 up to an. And then we define the characteristic polynomial of this differential operator by considering the following polynomial, which we denote by pt of x. And this is just a polynomial where we replace the ith derivative of f here by x to the I. And here there's a little clash of notations. So this word characteristic polynomial we already learned when we talked about eigenvalues. So if we had a linear map, then we could assign to this a characteristic polynomial, and then the zeros of this characteristic polynomial gave us the eigenvalues. But this here is now a different characteristic polynomial, but sadly it's also called characteristic polynomial, but it has nothing to do with the other characteristic polynomial. So this is a characteristic polynomial of a differential operator. And also notice that if I consider p of t of d, so by d I mean this differential operator which sends f to its first derivative. So this would mean we have ai di, d to the I, and again here by d to the I, so d is an operator, it's a map, I mean that I apply d I times, so this is exactly our operator t. I mean, this is how we define this characteristic polynomial. Okay. And this characteristic polynomial will now be used to calculate elements in the kernel of t. And for this we use the following proposition. So the statement is that the function e to the lambda t, so this is a smooth function, and the statement is that this is an eigenvector, or in this case also often called an eigenfunction, because we now talk about functions, but this space of smooth function is a vector space, and therefore this word eigenvector makes sense. So this is an eigenvector of this differential operator t with eigenvalue given by the characteristic polynomial of t evaluated at this lambda. And the second statement is that this function e to the lambda t is in the kernel of t if and only if this lambda is a zero of this characteristic polynomial. Okay, so let's prove this. So prove. So first notice that what is d of e to the lambda t? So what is the first derivative of e to the lambda t? Well, it's lambda e to the lambda t. So what is, if I apply this operator di times to this e to the lambda t? In other words, if I take the ith derivative of this, well, this just means that I get lambda to the I, e to the lambda t. Therefore, what is the differential operator t applied to lambda e to the lambda t? Well, recall here that the operator t just means we take this linear combination here with these operators d to the I, which is the characteristic polynomial of this operator t. So this is the sum. I goes from 0 to n ai, and now we apply di to this e to the lambda t, but this is just lambda I, so lambda to the power I, so this is I goes from 0 to n ai lambda I e to the lambda t. But this here is just the characteristic polynomial of t evaluated at lambda, and therefore this is pt lambda e to the lambda t. Therefore, applying this differential operator t to this function e to the lambda t gives this number times e to the lambda t, and therefore this e to the lambda t is an eigenvector for this linear map t with this eigenvalue here. And this eigenvalue here is the number we get when we plug in this real number lambda into this polynomial, this characteristic polynomial of t. And this is exactly the statement of the first thing here. And the second, I mean, because of number 1, we know that we have this. So when is this 0? So when is this element in the kernel of T? So when this is 0? Well, this here is 0 just if this coefficient here is 0, because this here is a function, a non-zero function, and therefore this is 0. Or even further, this exponential function is never 0 if t and lambda are real numbers, and therefore the only way that this here can be 0 is when this here is 0, and therefore we need that this p of t evaluated at lambda is 0. And this proves what we wanted to prove, because this function here is in the kernel of t if and only if the lambda is a 0 of this characteristic polynomial of t. Okay, so, and this gives us elements in the kernel of t by looking at its characteristic polynomial and find it's 0, and then e to one of these zeros will give us an element in the kernel of t. And yeah, so as a corollary of this proposition we get the following, that first, if we have n different real numbers, then these functions e to the lambda 1t up to e to the lambda nt, these are linearly independent. And then if the characteristic polynomial of some differential operator t has n distinct zeros, lambda 1 to lambda n, and t is now always a differential operator of order n, then these functions e to the lambda 1t to e to the lambda nt are a basis of this kernel of t. So these give us all possible solutions to the homogeneous equation t of f equals 0. So, and why do we get this? Well, the first statement, what do we use there? So we had this operator d, yeah, so these functions e to the lambda nt, so they are all eigenvectors of this differential operator d with eigenvalues lambda 1 up to lambda n. And now we assume that these are different eigenvalues, and then we had this theorem which was it was a proposition no, it was a theorem. So we had theorem 5.6, I think. In this theorem we proved that eigenvectors for different eigenvalues are always linearly independent. And here we now have eigenvectors of this operator d, which have different eigenvalues, and therefore by this theorem these functions, so meaning these eigenvectors or these eigenfunctions, are linearly independent. So this shows that they are linearly independent. And this we now want to use to prove the second statement. So first, for all I from 1 to n, if they are zeros of this characteristic polynomial, so this is what we assume here, then by the proposition we just proved before, this means that these functions here, e to the lambda 1 t up to e to the lambda nt, they are all elements in the kernel of t. And now by number 1, we see that they are linearly independent, because we now assume that they are different, and therefore these functions are they are linearly independent. And by this theorem, which we didn't prove yet, but we will use it here, so theorem 6.4 was a statement that the dimension of the kernel of a differential operator of order n is always n. So in this case here, the kernel, the dimension of this kernel of T is n. So in combining this, we have n linearly independent vectors in an n-dimensional space, and therefore they are a basis. So if we start with a differential operator T of order n, and we look at its characteristic polynomial, and we can find n different zeros of this polynomial. I mean, this will not always be the case. So this Pt is a polynomial of degree n, and it could happen that we find n different real zeros of this polynomial. Then we are already done to describe this kernel, because we can write down a basis of this kernel T, and we also see that in this case then the dimension of this kernel is n. But later we will see, also next time, what happens if we don't find n distinct zeros. Why is this statement still true, that the dimension of this kernel of T is n? But now let's finish with one example where this is actually the case. So for example, consider this a differential equation. So this is a homogeneous differential equation, because here is a 0 on the right. And we now want to find the zeros as the solutions of this equation here. And first, what is the differential operator corresponding to this? This is the operator d cubed, so the third derivative, and the d squared minus d plus 3, whereby this here, we mean 3 times the identity map. And therefore the characteristic polynomial of this differential operator is x cubed minus 3x squared minus x plus 3. And there we will do some examples how to find this expression here now. You can check that this equals x plus 1, x minus 1, x minus 3. So in other words, this polynomial has 3 different zeros, minus 1, plus 1, and plus 3. And then by the corollary, we see that the kernel of this differential operator has a basis given by e to the minus t, e to the t, e to the 3 t. And therefore the solutions to this equation here, so general solution, is given by f of t equals some multiple e to the minus t plus some multiple of e to the t plus some multiple of e to the 3 times t. And this gives all solutions to this equation here. And if there would be some function g of t here, we would need to find one particular solution, and then we could add this particular solution here. And yes, and also in the homework you will need to solve one particular differential equation. So there will be a g here, so you will need to find a particular solution, and then you consider the homogeneous equation. So you need to calculate the correct polynomial and find the zeros, and then find the homogeneous solutions. And then there will also be additional conditions. So for example, here instead of asking for all solutions to this, you could ask for the solutions to this with the additional property that f of 0 equals something, and then maybe also f prime of 0 equals something. And these conditions then you can check which of these c's you should choose here to get this solution here. So for example, if I would say I want a solution such that f of 0 equals 0, then I need to plug in 0 here, and I get that I get C1 plus C2 plus C3 equals 0. And then this condition would also, I would consider the first derivative of this, and then plug in 0 and get another condition on these C1, C2, and C3, and you get a linear system which you can solve. And then in this case here, you maybe get, instead of this 3-dimensional space of solutions, if you also want these two conditions, then maybe in this case you will get a 1-dimensional space. Yes. Okay, but next time we will then prove this theorem here, which states that the dimension of the kernel is always n, and also see somehow the extended version of finding elements in the kernel. So in other words, solutions of the homogeneous equations. And then maybe also do one more example. See you then.